Welcome to this PowerPoint video lesson on the graphical transformations of functions. So lesson number 2 on transformations, specifically where we're going to be introducing combined or multiple transformations. So first off, let's try to recap. I introduced these 8 different kinds of transformations in the first video. The ones on the left are where we have a function operating on the outside of the function, which changes the y values, and the transformations on the right, these operate on the inside of the function and are changing the x values. Specifically, I've reworded transformation number 8 very slightly, so the modulus function applied on the inside of the function, we ignore the part of the original graph where the x values were negative because the mod of x that now enters the function, the mod of x can never be negative. And we're not just reflecting the positive x values, we're actually reflecting the part of the original graph where the x values were positive. That part of the original graph is reflected across the y-axis. Okay, so first off, let's revisit this transformation y equals f of kx with k multiplied by x inside the function. So this is our test yourself question last time where we had this cubic function f of x with x plus 1 inside brackets, all cubed, plus 1. And we said, well, what is this graph going to look like after applying a transformation f of half of x, or half of x inside the function? So where this k in our transformation f of kx, with this k inside the function is a half. Okay, so we said that f of kx is a compression in the x direction by a scale factor of k. So that's going to be a compression in the x direction by a scale factor of half. Actually, this is equivalent to a stretch by a scale factor of 2 in the x direction. So after this transformation, our original cubic function in red, it's going to be transformed onto this blue curve. I've got a table of values with x values bounded between -4 and 2, and the corresponding f of x and f of half of x values. The point that was originally at 1, 9, that's going to be stretched. The x value is going to be stretched from 1 to 2, and it's going to go on to 2, 9. The point that was originally at -1, 1, again, the x value is going to be stretched from -1 to -2, and the point shifts onto -2, 1, and the original x-intercept for the curve in red, f of x, the x-intercept is going to have its x value also shifted from stretched rather than shifted from -2 to -4. The only invariant point is going to be the y-intercept, where the x value is 0. It doesn't matter what we scale the x value of 0 by, anything multiplied by 0 stays at 0. So the y-intercept stays at 0, 2. Okay, so our first example with combined or multiple transformations. Okay, so here we have a transformation with two transformations from y equals f of x to y equals 2 multiplied by the whole of f of x plus 3 inside the function. Also, we're actually going backwards in this question. It's telling us that the point AB is being transformed onto the point -6, 4. And the question asks us to find the original point AB. So we need to go backwards. Okay, so we have two transformations. The transformation that's f of x plus 3 inside the function, we know that that shifts 3 to the left. So if we're going back from -6, 4, if the x coordinate is going back to A on the original point, capital A, then we need to actually shift 3 to the right, which means that -6 needs to shift back 3 to the right to -3. And the other transformation, which is a stretch by a factor of 2 in the y direction, if we're going back to the original point on y equals f of x, then it's the y-coordinate that actually needs to be compressed by a factor of 2. So the y-coordinate 4 needs to be compressed by a factor of 2 to 2 to give the original y-coordinate b on the original point, capital A. So now we've got this new, or the original point A, capital A, as minus 3, 2. Minus 3 for little a, 2 for the y-coordinate, little b. We can check our answer because if minus 3, 2 is the correct original point, then if we stretched it by a factor of 2 in the y direction, the y-coordinate would go from 2 to 4. And also we would need a 3-unit shift to the left from minus 3 to minus 6. And that affirms our answer. For two things that are important to note. One is that actually it doesn't matter what the original function was, as long as the transformations are applied and as long as we understand the transformations in the right way, the same corresponding point has to be transformed in this way after we apply the two transformations or any set of transformations. Okay, so it actually doesn't matter what the original function was. We have an infinite number of different possible functions, in fact, where we have this point minus 6, 4, that the original point A is transformed to, in fact. Also, it's important to know that in this question, actually it doesn't matter which order we apply these two transformations. One's applied inside the function, and the other one's applied outside the function. So the first step process of getting to the answer, I reasoned through the translation first, and then the y direction stretch or compression. The check, I'd actually checked it the other way around by checking the stretch in the y direction and then the shift to the left. Okay, so actually, if we have two transformations, one's inside the function, one's outside the function, the order doesn't matter. But in a second, let's see an example where the order does matter. Okay, so this is an example that I really like with combining transformations because it links to this trigonometric identity that we don't see or use all that much. So this trig identity is where in either form where we have the sine of 90 degrees minus x, this is always equal to the cosine of the angle x. And the other version, sine x, is also always equal to the cosine of the complement of the angle x. Okay, so the complement means that these two angles sum to 90 degrees. Okay, so if we set up the basic right angle triangle, this identity seems to make a lot of sense because I've set this right angled angle with right angle triangle with the angle little x, and the other angle other than the right angle must then be 90 degrees minus the angle x, because all three angles have the sum to 180. So if we take the cosine of x, I've labelled A as the adjacent to the angle x and h as the hypotenuse. Well, this is actually also the same as the sine of the angle 90 minus x, because the side A is in fact the opposite in relation to the angle 90 subtract x. Also, we can see that the sine of the angle x, where we have the opposite over the hypotenuse to this trig ratio, that's also the same as the cosine of the angle 90 subtract x, because the adjacent is the side O, the opposite relative to the angle x, divided by the hypotenuse. So this trig identity seems to make a lot of sense, but it's also not restricted actually to just right angle triangles. So to prove our point, if we think about it, we're starting with sine x. Inside the function there appears to be just two transformations, right? And if we think about it in the right way, it should be going to cosine of x after these two transformations. But which way around do we apply these two transformations? Okay, so if we start with f of x is sine x, option number 1 is to first apply f of x plus 90 inside the function, which we know is a shift to the left by 90 degrees. And if the original function f of x is sine of x, this is the same as the sine of x plus 90 inside the function, and that's also the same as the sine of 90 plus x inside the function. So the other transformation is this reflection of the y-axis, g of minus x. And we're thinking, well, if we apply this transformation second, if we think about it carefully, the minus x replaces everywhere we had x in the function before. So it just goes in to just replace the x. So we have the sine of 90 subtract x. Now, after these two transformations, so first the shift left by 90 degrees, and then the reflection in the y-axis. Well, we have option number 2. We only have two transformations. They can only occur either way around. The other way around is to do the reflection first. So we have f of minus x. There's nothing really wrong with this because it's just the sine of minus x. But now we need to be extra careful because if we apply the shift second, so I've called the sine of minus x s of x. So if we have the s function of x plus 90 inside the function, now we have a problem because if we replace everywhere we had little x before in the original sine of minus x function, if we replace the x by x plus 90, we're actually taking the negative of the whole of x plus 90. So if we apply the two transformations this way around, we actually end up with the sine of minus x minus 90, not the sine of 90 subtract x. Okay, so let's try to get rid of this incorrect way of doing it and remember the correct order. In the correct order for transformations inside the function, we actually have to apply shifts or translations first before we reflect the x values or stretch the x values. Okay, and with the graphs, so we're starting from the red sine curve, we're trying to go to the purple cosine curve, starting with the red f of x, sine wave. We're applying our 90 degrees shift to the left. Desmos only works with radians, so pi by 2 radians is the same as 90 degrees. We're shifting 90 degrees or pi by 2 radians to the left, which takes us to the blue g of x curve. And then we're going to apply g of minus x, which is a reflection in the y-axis, which actually doesn't change because the blue g of x function is symmetrical about the y-axis. So after we reflect it about the y-axis, we can check that h of x is indeed the same as the cosine wave cos of x. And we're back to the purple curve that we wanted. Okay, so which does show us that if we apply our principles of the transformations in the right order, a lot of different parts of mathematics, they all do come together. Thank you for watching.